So, good evening and welcome to Space Place. I'm going to take this opportunity tonight to talk about what we can look forward to in astronomical events in the coming year, in 2025. There's a lot of talk just lately about some planetary alignments, and I think I'll start with that. I'm going to be using Stellarium, which is a piece of free software that you can easily download. It runs on Windows and Macs and Linux, and is quite capable. It's free software. It's very, very capable. It's as capable as a lot of the stuff that you would pay for. And so let's talk for just a minute about the Great Alignment, which has been given some kind of arbitrary dates. Lately, there's no particular date. What's going on here is that the only thing that's really special about this, I should say, is that the planets, except for Mercury, and not Pluto, if you still count that as a planet, are all the planets, and of course not Earth, because we're standing on it, are above the horizon for a little while after sunset. So here's actually the sky right now, as it, oops, that's not the right button here. There we go. That's the button we want. So over here is Venus, and here is Saturn, and up here is Jupiter, and over here is Mars. This line is the plane of the solar system defined by the Earth's orbit. We call it the ecliptic. And the planets are always on the ecliptic. That's your alignment. In other words, there's never a time when the planets are not aligned along the ecliptic. So there is no alignment. What is interesting is that these planets, as well as Uranus and Neptune, which are kind of out here somewhere, but you can't see those without a big telescope anyway. So we have, if you go out tonight, you have Venus and Saturn and Jupiter high overhead there, and Mars, which the moon occulted last night. So having them all above the horizon at the same time, that's the kind of cool thing. That ends, of course, as soon as the westernmost of the planets, here, in this case Venus, sets in the west. And then you lose Saturn pretty soon after that, and so on. So in the specialness of these days until whenever this is in February, that the sun sort of begins catching up with Venus and Saturn there, is that they're above the horizon at the same time. But they're scattered all across the sky from, as you can see, all the way from over here in the southwest to over here in the east. Now, let's turn this off, though, and then take a little closer look at Venus and Saturn, because they are going to do sort of an interesting little thing here in the next few days. Not anything of any great cosmic significance, but let's zoom in on them a little bit. And so I'm just showing you, I'm just doing basic things here with Stellarium. I'm just going to step ahead a day at a time. So here we are on January 14th. You see Venus highlighted with the little bars there. You can see that, right? And Saturn right up here. Let's just advance a day. And you see Venus and Saturn got a little closer. Let's advance another day. And another day. Where are we now? The 17th. And another day. There we are on the 18th. And I think the 18th is when they approach most closely. Now, notice you're still seeing a lot of sky here. There's the southwest and there's the west. This is a big chunk of sky. But Venus and Saturn will make kind of a nice grouping over there for a night or two. If we just keep on going here to the 19th and then the 20th, they start getting farther apart again. Now, I think I checked, and at closest approach, they're still about 2 degrees apart. And a degree on the sky is actually a fair amount of space. The full moon is about a half a degree. So these things are 4 full moons apart in the sky. That's a pretty, you're not going to take a telescope to separate these things. But they will make a nice sight in, say, binoculars or something like that. Your telescope will have too small a field to have both of these in there. But binoculars, typical binoculars should do it. So that's not an alignment of any sort, nor is it a conjunction. It's just sort of a close approach of these two planets. But that is coming up here just in the next 2 days. And as I mentioned, the last night, so we want to go back to the 13th. Last night, the moon occulted Mars. So we had a, if our talk had been 1 day later, we'd be talking about what would be happening tonight. But Stellarium will imitate this simulate this, I guess I should say, quite nicely. So we can go back in time here. And if we just sort of center on Mars. So here we are at about a little bit after 7 p.m. last night on the 13th of January. And I'm just going to advance time here. An hour will be probably too much. I'm just going to advance by the minute. So you can see the moon approaching Mars there. So this is just advancing a minute at a time. So this is kind of a speeded up, sort of a time lapse, if you will. And a little bit after 8, by the time that we get to a little past 8 p.m. last night, we'll see the occultation happen. So, oops, sorry, that was too far. That was an hour. I wanted to go minutes. There we go. Did anybody see this last night? I went out and took a very bad picture of it, very bad photograph. So there we are. You'll see Mars disappear here. Any click, there it goes. Okay. So by 10 after 8, 11 after 8 last night, the moon had moved in front of Mars, and about an hour later, by an hour later, the moon had moved far enough, and now I'll jump ahead an hour. The moon had moved far enough that Mars was emerging from the other side, well, an hour and 10 minutes or something like that. So that was last night's occultation, one of the few good occultations of the year. In fact, I don't know of any other nice occultations that are going to be visible from Madison. But those are the special events. So January has some nice stuff. Occultation already passed, all the planets in the night sky not in alignment, and then the not a conjunction but a close approach of Mars, of Saturn and Venus just in the next few nights. So we'll have to hope for that we have some nice clear nights that are not too cold to go out and enjoy some of the night sky. So I'm not going to talk too much about constellations unless we have extra time at the end, because the constellations are pretty much the same every year, and really what I want to talk about is the things that are special to this year. So let me go to my slides and start just by giving you some suggestions about information sources. Occasionally I'll point at something in the sky and say, oh, that's Jupiter, and somebody will say, how do you know? Well, I know because I look it up in these sources here. None of this is secret information. In fact, I highly recommend that you take a look, for example, at it. This is an annual publication, the Astronomical Calendar of 2025, by a guy named Guy Ottewell, and you can find his website at universalworkshop.com, where he sells his calendar, which you can also get electronically, and it gives you really a day-by-day guide. It's kind of an almanac, and a day-by-day guide to what's happening in the sky, organized by month, and then there's a section at the end on, say, eclipses and meteor showers and all that kind of stuff. It's really a great go-to source. It's the first thing I will turn to when I'm looking for what's going on in the sky. And then the next thing, I was just demonstrating Stellarium, which I highly highly recommend down there as well. Then there are some things. This is just an alternative. Skylive.com is not too bad. And then a couple of eclipse sites, which aren't going to be, as I'll talk about, not going to be all that important this year, but they're good sources of information. And then I like to recommend spaceweather.com because it's basically a NASA site, but space weather includes lots of information about solar activity. That's their primary concern, is solar activity, and so you can often get a warning of a day or two about good auroral displays. And if you're just interested in sunspots and solar flares and things like that, that's all there as well. And then finally, just for fun, I look at it every day, every morning, the astronomy picture of the day, the APOD. also from NASA. So that's just a nice some sort of little dose of astronomy. They choose some usually really spectacular image related to astronomy, not always a sky image or anything, but some sort of astronomically related image. Oh, and I'll talk a little bit towards the end about T Corboreal, T Coronae Borealis, which we're still waiting to explode. It was supposed to happen last year, but maybe it'll happen this year, and you can get information about that on space weather too, so I'll mention that a little bit later as well. So let's talk about just some of the basics, the things that define what's happening in astronomy this year, such as the solstices and equinoxes. And we, of course, already had the astronomical year. If we kind of begin that with the winter solstice, then that's already back in December. But the effects of the short days of winter and the solstice, the winter solstice for the northern hemisphere, the winter solstice, that effect does linger until next year. It's sometimes surprising to realize that although that's the shortest day, December 21st there, that the latest sunrise, you'd think that the shortest day would be when the earliest sunset and the latest sunrise happen, but they actually don't, because we fail to use sundials anymore for keeping time. If we did, that's exactly what we would find out, is that the day of the summer solstice is the day of the latest sunrise and the earliest sunset. But because we don't use sundials, but instead use mechanical clocks, which actually keep time differently, the rate of the clock, when noon on the clock, does not coincide to noon on a sundial, and can be off more than 15 minutes at various times during the year, and that shifts sunrise and sunset times against the clock. And so our latest sunrise was actually back on January 4th. So that was in this year. Last year was a leap year, but this year we're not going to have a February 29th, and I'll talk about that in just a minute when I get down to the vernal equinox here. And then one thing to watch for is, of course, the daylight savings time begins there on the 9th of March. So the solstice was back actually technically last year. Well, not technically, was actually last year. But the vernal equinox, which is actually when we usually start sort of the astronomical year, traditionally societies often counted the vernal equinox as the beginning of the year. This was true in Europe for quite a long time. So at any rate, when does that happen? That happens at not quite 9. This is universal time. I'm just going by the universal time, basically the time in London, when not in the summer. But this makes it relatively easy for us to calculate time differences, which is all I'm interested in right here. So it happens at 8:59, 9 hours UT, call it. But last year it happened at about 3 hours universal time, or about 6 hours earlier. So we're 1 year later, but the vernal equinox happened 6 hours earlier last year. It's convenient that we did a leap year last year, because now we're going to now accumulate time until we have an extra day, and then we're going to add in the extra day in 4 years, in 2028. So why do we have to add that extra day? Well, you see it right here, because this 6 hours that the vernal equinox has slipped back. It's 6 hours later this year than last year. It's going to be 12 hours the following year, and then it's going to be another 6 hours, 18 hours, and then it's going to be 24 hours by 2028. And the vernal equinox will be occurring a whole day late, because the real year is closer to 365 and a quarter days, and that's the quarter day that you see there, that 6 hour difference between last year's vernal equinox and this year's vernal equinox. So if we didn't make that correction, then this is the essential point of the Julian calendar, which goes all the way back to Roman times. The Julian calendar inserts that extra day every 4th year. So we have this leap year when we have an extra day, and then that fixes what would otherwise be a shift of the vernal equinox through the year of about Well, every 4 years we would slip off one day of the vernal equinox.
The Julian or the Gregorian?
That's the Julian, because it turns out that that one day every 4 years is a little bit of an overcorrection. And so the Gregorian calendar, instituted in 1582, drops a leap year every 100 years, a leap day every 100 years. So in 1900, which should have been a leap year, they skipped it. So that's the Gregorian rule. In century years, you skip that, so that helps undo the overcorrection of inserting the day every 4 years. But that's an undercorrection. And so you have to add an extra day every 400 years. So in years divisible by 400, such as in the year 2000, instead of skipping the leap day, we include it. So it's a series. It's an arithmetic series approximating the true length of the year. Those time differences are, we would have to look at much longer spans of time to start measuring those. But this is the root of the problem right here, is that the equinox, that the true year is closer to 365 and a quarter, and we only count whole days. So there you see that operating there. Of course, we'll get then into the summer, which we're all looking forward to, I think, at this point, when it's now in the single digits out there in Wisconsin. Look for the longest day and the shortest night here on the 21st of June. And we get a similar sort of thing, once again, because we're so foolish as not to use sundials anymore to keep time. And so the earliest sunrise and the latest sunset also don't correspond to the solstice either, and for the same reason that the winter solstice and the equinoxes, for that matter, are off by a certain amount. So the latest sunset is actually on June 27th, and the earliest sunrise is actually before the solstice on the 14th of June. So they kind of bracket the true solstice there, earliest sunrise and latest sunset. And then, of course, out here in the summer, in the northern hemisphere summer, this is also when we reach aphelion, Earth's greatest distance from the sun, which may seem counterintuitive, but because we're farthest from the sun, yet that's our warmest season, but that's because the distance of the Earth from the sun is actually not an important factor in our climate. It's all got to do with the inclination of the hemispheres of the Earth with respect to the sun, not the actual distances, because the distance difference is not very much. So even though the Earth is farthest from the sun on the 3rd of July, it's still summer up here. And then finally, I'll skip through the autumnal equinox here and get down to where we started, kind of a year from last year's winter solstice down here on the 21st of December. And this is a diagram that I swiped from Ottawell's astronomical calendar here, just illustrating the basic geometry that we're talking about here. I'm not going to go through all of this at all. This might remind you of kind of a medieval astronomical instrument. It actually, in a sense, is. But this is the kind of thing that Ottawell doesn't want to let you get away without thinking about, is the geometry of these important celestial events that define our life here on Earth. Okay, well, let's talk about something. You can't really easily observe equinoxes and solstices, or you can observe them if you want to, especially with a sundial. But let's talk about eclipses. Last year, 2024, was a big year for eclipses. We had a spectacular solar eclipse in April last year, as you'll no doubt remember. This year, the solar eclipses are not really too much to talk about. I'll show you what the details on those in a minute. And instead, what we're getting are 2 total lunar eclipses. This is another diagram from Ottawell. This is showing you the Earth orbiting around the sun and the moon orbiting around the Earth. So the blue disk is the plane of the moon's orbit. And the plane of the moon's orbit is tipped with respect to the plane of the Earth's orbit. So this is the Earth's orbit out here. And he's showing you that by the light blue and the dark blue, he's showing you the tip of the orbit with respect to the sun. So that border there is basically the line, the intersection of the plane of the moon's orbit with the plane of the Earth's orbit. And as the moon orbits the Earth, that plane remains fixed, almost, with respect to the stars, to the rest of the universe. So just look at the moon orbiting around here and notice that that line, the border between the light and the dark blue, remains sort of horizontal on our screen all the way around. It's not changing its orientation. Well, the only time you can have an eclipse is when that line, which is called the line of nodes, that line, that intersection of the plane of the moon's orbit with the plane of the Earth's orbit, if that line points to the sun. So when we have the moon, when we have the Earth over on this side of the orbit, where the line of nodes is roughly pointing towards the sun, in that period of time during the Earth's orbit, that's called an eclipse season. And those are the only times you can have eclipses, because over here, when the moon is full, like it is here on this side of the Earth's shadow can fall on it. It can move through the Earth's shadow, and we can have a lunar eclipse. Or when the moon is on the sun side of the Earth, the moon's shadow can fall on the Earth, and we can have a solar eclipse. So these are the only two times, here in this case in March, and then about 6 months later when the Earth gets around to the other side, that's the other time we can have eclipses. So it's only when the line of nodes aligns roughly with the sun that we can have eclipses. So it'll probably occur to you that we don't always have eclipses in March and September. And the reason is that while this line of nodes remains almost fixed, at least during the period of maybe one orbit, it's actually shifting. It's precessing. It takes about 19 years to go all the way around. So during a period of 19 years, the eclipse seasons will rotate all the way around the Earth's orbit. And so we will have eclipses sometimes over here in January, for example. But that will be at a different time during this 19-year cycle. It's actually about 18 2/3 years as the line of nodes of the moon's orbit rotates around. For any given year, we can pretty much ignore it. Well, not if we're doing detailed calculations. But in this case, for this year, we can just say if we're having eclipses in March, then we're likely to have eclipses 6 months later in September. Those will be the two eclipse seasons this year. So what we get, for example, the first thing that we get is a nice lunar, total lunar eclipse on March 14th. So the full moon, right over there, the full moon will be will move through the Earth's shadow. So the alignment is pretty close. It's not perfect, you'll see in just a minute, but it's close enough that the moon moves through the Earth's shadow and we see a nice total lunar eclipse. Now, 2 weeks later, since that's full moon, 2 weeks later, the moon will be new over on the sun side over there, and that's when you can have a solar eclipse. But in 2 weeks later, the nice alignment of the sun, Earth, and moon that produced the total solar eclipse is now off by a bit because the Earth has moved for 2 weeks in its orbit. So you can't have a perfect solar eclipse 2 weeks after a perfect lunar eclipse because the alignment was right at the total lunar eclipse. So the only thing we can get 2 weeks later, sometimes it's 2 weeks earlier, is a partial solar eclipse, and that's what we get this year, a partial solar. It's actually even worse than that. It's a partial solar eclipse, which a lot of people don't even bother to observe, but it's also a partial solar eclipse that only is visible from the polar regions of the Earth. I'll show you a chart of that in just a minute too. So this will be a really nice lunar eclipse right here, which is actually going to be visible for us here in Madison, because the other thing that has to happen is you got to be on the right side of the Earth to see that lunar eclipse. If it happens during your daytime, then you're not going to see it. But it is going to happen for us for our nighttime. And then 6 months later, we get another total lunar eclipse right over here. And of course, that automatically means that the corresponding solar eclipse has got to be bad. And that's the case. 2 weeks later, we get a partial solar eclipse there. But that's then the rough, the rough geometry of these things that we'll look at in more detail here. So we get 14th March, we get a nice total lunar eclipse that we can see in the This is the best event of eclipses for this year. This is the best one for us. The lunar eclipse there in September, we won't be turned the right way to see that. That will be visible only in the Indian Ocean, so take a cruise and you can see that one. And then we have two solar eclipses, two partials. So this is our nice lunar eclipse. Again, this is from Guy Ottewell. You look up all the details of these eclipses there. And it will be happening beginning kind of late at night, almost 11 p.m. In our time zone. So it'll be a late one that will not even be full until well after midnight here at almost 2 a.m. is when the moon will be most immersed in the Earth's shadow. So this shows you the dense part of the Earth's shadow called the umbra here, and the moon is not perfectly aligned. If that had been a perfect line from center of the sun to the center of the Earth to the center of the moon, then the moon would be right here centered in the Earth's shadow. So the alignment's not too bad. We get good immersion of the moon into the Earth's shadow, into the Earth's umbra here. So we'll get a nice lunar eclipse if you don't mind staying up till early hours of the morning to see it. So that's our best eclipse, our only good eclipse for this year. So the other ones look like this. So we have one other, here's the lunar eclipse down here, and this is not showing the kind of diagram before, but this is showing you where it's visible on Earth down here. And there's the center of the eclipse right there, and you can see that you got to be out here in the Indian Ocean. So we're way on the other side of the Earth. We're just not facing the right direction to see this, what would be a perfectly nice lunar eclipse if the Earth turned us the right way. The solar eclipses, I don't think you're going to want to travel to see these. They're both partial eclipses, and then this shows you the track of the eclipse up here. This is for the March 29th one, and you can see the shadow of the sun, the shadow of the moon, excuse me, and the dark part of the moon shadow never even reaches the surface of the Earth anywhere. So this is just the partial shadow, the penumbra, that crosses out here ultimately in the North Atlantic and there out around the North Polar regions. And then we have almost the opposite case for the one in September, the September 21st. Oh, I guess that's on the equinox. There's an equinox partial solar eclipse, but once again, it's partial. No part of the umbra touches the Earth. We just have the partial shadow of the moon, and it's crossing out here across the Antarctic Ocean and Antarctica. So those, you won't see anybody buying cruise tickets to go see either of these eclipses, but that would be the only way you'd get out there probably to see them at all. So in summary, one good eclipse, it happens in March. And it's a lunar eclipse, one good total lunar eclipse this year. The rest of the eclipses are pretty much of little interest for us here in Wisconsin. All right, so let's talk a bit then about what the planets, so that's the sun and the moon, what the sun and the moon are doing. Let's talk a little bit about what the planets are doing. And I'm going to go back to Stellarium for this and use Stellarium to simulate what we're going to see, first of all, in the evening sky. We've already started a little bit of that just a few minutes ago, but I'm going to carry it through the rest of the year. And then what we're going to see, we'll switch around and look into the east and look into the morning twilight sky. So we talked already briefly about the non-alignment of having all the planets except for Mercury above the horizon at about the same for a little while, for an hour or two in the evening sky. But by February, Saturn, which is going to get Venus is going to move past Saturn, as we saw there. They come close together, and then Venus moves past. Then Saturn will be the first one setting in the west. Once Saturn goes down, you don't have all the planets except for Mercury above the horizon anymore. Anyway, so that's going to by late February, as you'll see, we won't have Saturn at sunset. And then we steadily, we do get a little look at Mercury. I guess the best look at Mercury in about June. Mercury is very seldom seen because it's always low on the horizon, and never stands out very much from the twilight. So you usually have to take some special steps. If you want to join the club of people who've actually seen Mercury in the sky, then you have to probably go to some trouble to find a low horizon. There'll be an okay elongation of that in June, as you'll see in just a minute. And then by summer there, by June, we'll have lost Jupiter out of the evening sky. And then by late August, Mars out of the evening sky, and we'll be back to kind of what we had last year for a good spell in the summer, where we have no bright planets in the evening sky whatsoever. But of course, what isn't in the evening sky is often in the morning sky. So then we'll turn around and take a look at the morning sky, and you'll see a good bit of planet activity over there, including Mercury in August. Once again, another chance to see Mercury. So let's go back to Stellarium and take a look over into the western sky. So I'm going to zoom us over to the west. And then what I'm going to do is jump to twilight. And this is another nice thing you can do with Stellarium. You don't have to just advance, say, hour by hour or day by day, but we can go to twilight every day and watch how things are changing in the evening sky. I'm just going to turn off, there we go. All right, so here we are looking over in the west, and this is basically tonight. And we can start advancing time one day at a time and watching how the sky will change. So we have kind of a time lapse now of twilight. You'll see the moon zoom by there. You can keep track. If you look down here, you can see we're now at the 3rd of February. And so you see Saturn disappearing into the twilight there. So by late in February, Saturn will be going down, not quite with the sun, but very soon it'll be going down with the sun. We'll still have Venus over there and Jupiter. Now this is all because as the Earth is orbiting the sun appears to us to be making its way along the ecliptic this way. So it catches up, so to speak, with these planets. Venus is orbiting around the sun inside the Earth's orbit, and so it has spent some amount of time coming up from behind the sun, and it's turned around, it's going to go back and cross between us and the sun. That's what it'll be doing when it disappears down to the horizon. So we'll just advance for a little bit here. We see there's Mercury appearing for just a little while, and then you're going to see it leave real fast. And there it goes. So for just a little while, Mercury and Venus over there on about March 11th. Mercury and Venus will be over there low on the horizon. Now, just another Stellarium trick. So how high above the horizon is Mercury right now? If we click on Mercury, Stellarium is going to tell us way more than we really want to know. But it'll tell us the altitude above the horizon is 11 degrees. So your fist at arm's length, the width of your fist at arm's length, that's about 10 degrees, give or take. So if you imagine the horizons, you're looking west, maybe over got a cottage on the east side of a nice big lake. You're looking out over the lake, and the lake shows you where the real horizon is. You put your fist on the lake, Mercury's that far above that horizon. So if you got some hills or trees, you're probably not going to see it. But if you find yourself a nice place, then this is the time to look. And it's in strong twilight. It's never not in strong twilight. And so your binoculars will help. But I've always wanted, I've never done it, I've always wanted to have some special pins made up for people who've actually seen Mercury, because it's very rare that anybody's actually seen Mercury with their own eyes. So this is your chance, at least in the evening sky. You'll have to wait and try it in the morning sky or another time if you miss this one, and it could be cloudy. So we're going to lose Venus and Mercury here by late March. And notice how much lower, we've been going a day at a time now. Notice how much lower in the western sky we now have Jupiter. If we went outside right now and looked up at Jupiter, we'd see it really high overhead. By twilight here in late March, it's going to be heading down into the west and soon to be followed by Mars as well. So let's just keep on going. There's Mars. You see the moon swing by every month. So once we get past June, the evening sky is going to be bereft of bright planets. So here we have Mars, which is not very bright by this time anyway, just about disappearing into the western sky. So that's pretty much the planet, the evening planet view. From there on over, there are no bright planets in the sky by summer. I guess I got to early July there. So that's kind of a preview there, what'll be happening in the western sky at twilight, which is when most of us probably do our stargazing. But let's go back and take a look at what happens in the morning sky, because what's not over here in the evening sky is often, not always, over in the morning sky. So we'll do the same thing. We'll go to morning twilight. Now, morning twilight, there aren't any planets over there. It looks like Mercury is really low down there, because they're all over in the evening sky, as we know. That's the great alignment that's going on, supposedly. But if we start now advancing, we're going to have to go a few months, though, because we need to have some of those planets make their way over into the early morning sky by having the sun move past them so that they're west of the sun, which means they come up before the sun over in the east. So we'll just advance here. And we're going to have to get somewhere. There we go. There's Venus. So the sun has moved past Venus, and Venus has ended up on the west side of the sun, so it comes up before the sun. And here it is early in the morning sky by April. So the first bright planet we're going to see in the early morning sky, if you're a morning person, you're not going to see any planets over there until Venus pops up over in April. But things will start getting more interesting because Saturn is still fairly close to Venus over there, so it's joining. Mercury pops up just briefly over there in the eastern sky. Venus makes its appearance, and then because, again, Venus is inside our orbit, closer to the sun, so Venus swings out there, but it's going to turn around and move back in, because from our point of view, Venus is never doing anything but going east and west of the sun, and that's what it's going to do right now. It's going to make go around in its orbit and start heading back down towards the horizon, as you can see, heading towards the sun, which is over here about now. So we'll get to late summer, and then we have Jupiter joining in the early morning sky, so not until July. We get Venus and Jupiter in the early morning sky. Well, that looks like that might be an interesting grouping just right there. I didn't notice that before. Let's just, when is that? So that's August 13th. Let's just take wonder how close they'll get. Probably not terribly close. Let's go back one day. Not too bad. So that's one to mark on your calendar. I'll mark that on my calendar. August, not April. August 12th, as we get around there. That might be worth getting up for to get a nice picture of that. That'll be a good binocular. Again, those will be too far apart to see in a telescope, but that could be a nice binocular. Well, that's 5:30 in the morning. Yeah, it should be. Yeah, UTC -5. It's switched to daylight time, so yeah, it'll be 5. Okay, so let's. So as we proceed on there, just to see what the rest of the morning says. So Mercury, here's Mercury's other appearance, and it pops up above the horizon here for a little while towards the end of August, but you'll see that it goes, I'm just going a day at a time, so it's not there for very long, and then it heads back down. Where was it at its highest? Is about there. Let's just click on it here and see how high it is above the horizon. So it's 10 degrees. It's never more than about 10 degrees above the horizon. So maybe your cottage is on the west side of the lake and you can look out that way. This would be your time to catch that in late August. So at what comes around eventually is we of course lose Mercury. We eventually lose Venus. It's got to head back on its way around the sun, and we're getting now Jupiter and well, we don't have Mars yet. Saturn must be up there. Saturn's already gone by. Anyway, so we start getting some bright planets in the early morning sky, but not till much later in the year. This is now late September, and we have Venus and Jupiter bright in the morning sky. So those are just some sort of previews of what's going to be happening in the morning and evening sky with the planets. We lose Venus again by November, and it looks like there's going to be another Mercury morning apparition there in December, when sunrise will be a little bit later, so maybe more convenient if you're, of course, you won't be at your cottage on the lake by then, probably. But so that's a little preview of the what's happening with the planets. Now, one interesting thing about the planets, well, let's see, let's not put it quite that way. The time we usually want to emphasize looking at the planets are when they're brightest, which is when they're closest and biggest. And so, for example, with Mars just passed opposition. Well, actually, no, Mars is at opposition just a couple of days from now on the 16th. So right about now, when you see Mars rising over in the east, over in the eastern sky, and in fact, let's go back and just do that. Let's return real quick to tonight. So here we are now looking east. The moon occulted Mars last night, so it's moved past Mars in its orbit there. But there's Mars. It's easy to spot over in the eastern sky, one of the brightest things over in that general area. It's right next to the two bright stars of Gemini, Castor and Pollux, right there. And in fact, I guess looks like one, maybe if we go another night ahead to the 15th, yeah, they're going to be pretty closely aligned. So there'll be a nice little band of three objects there, Castor, Pollux, the two stars, and the planet Mars, maybe looking a little bit like the belt of Orion over there. So that's kind of nice. So this is about the best time to be observing Mars because we are closest to it at opposition. Opposition is when what it's opposite to is the sun. And so as the sun is setting, Mars is rising. So Mars is up all night. And it's brightest and biggest. So those are the times we look for to observe the planets. Jupiter, we get an opposition typically every 13 months or so. But that means occasionally there's a year when the opposition happens so late in 2024 that there won't be one in 2025, and we'll have one early in 2026. That's what's happening this year, is we don't get any opposition. Jupiter skips opposition this year. So there will be no best time during the year. Well, there will be a best time, but there won't be an opposition to go see Jupiter this year. So that's not anything too remarkable. It does happen from time to time. Saturn is also going to do something interesting that we also can't see, and that is that the Earth is going to cross through the plane of the rings of Saturn. So once again, stellarium is the way to look at this. Let's go back around here and find Saturn. Here's Saturn. Now, stellarium will do a pretty credible job of pretending that it's a telescope. And it'll tell you things your telescope won't tell you, like the names of the moons and things like that. Now, here we are looking at Saturn, and we can see the rings in the Washburn telescope. You would have a view not too unlike this. You easily see the moons on either side. And that telescope is big enough that even when the rings are as they are, not quite aligned there, but fairly thin, they'll show up in that big telescope. Let me make just a couple of quick adjustments here so that I can be adjusting the time more freely. All right, so here we are. This is basically tonight, looking at Saturn. I want to go back a year, and what I hope will happen is that you'll see basically the same view, but you'll see that the rings are tipped. I'm just going to go back to 2024. Watch the rings. Notice the tip of the rings. Oh yeah, that worked pretty well. Let's go back another one. Okay. A couple of years ago, if you were up at the Washburn telescope, looking at Saturn, you would see the planet, and then the rings were nicely tipped this way. And also, they're tipped towards the sun in such a way that, so we're seeing the sun illuminated side of the rings. You can imagine that if you were back here on the other side looking up at the rings, where they're in the shadow, they're in their own shadow, they wouldn't be as bright. So we've had a nice view of the rings for the past few years, but as Saturn is moving around in its orbit, kind of like the way the nodes of the moon's orbit have to line up, at a certain point, the plane of the rings, the plane of the orbit, the plane of the rings will be in the plane of the Earth's orbit, and we'll be looking edge on at them, and that's what's happening. So let's go back now, 2024, 2025. So it's actually going to happen here in the next couple of months that we're going to see the rings of Saturn edge on. And so I'm just going to start going a day at a time. The moons are going to zoom around all over the place, because I'm going a day at a time. They're orbiting on periods of a few days, so they're going to scramble themselves all around. But see if you can keep an eye on the rings. So here we are going into February. Can you see that? Let me go and zoom in just a little bit more here. You see that the rings are getting narrower? So by March, okay, there we are. Okay, middle of March. By the middle of March, they're almost edge on, because the Earth is now in the plane of the rings. That is, as we're orbiting around the sun and Saturn gets to the right place, we're in the plane of the rings. This won't last forever, of course, because it's going to keep on tipping, and we're going to be out of the plane, and now we're going to be looking at the dark side, the unilluminated side of the rings. Well, we're actually not going to be looking at them, because unfortunately here, when this is happening in mid-March, let's just go back to where, turn on the, I don't want that, I want the, well, we'll just zoom back. There we are. Saturn will be too near the sun. It'll be up in the daytime sky when all this is happening. So solarium is actually one of your few ways to actually see this happen, because we won't be looking at it with telescopes or anything. The whole ring crossing thing this time around, this can happen also far away from the sun, and that's when we've often seen Saturn's rings edge on. But we're going to miss it this time, this ring, this alignment of our line of sight with the rings. We're going to miss it because it's all going to happen over there fairly near the sun in the sky in later on in March. So let's just zoom in though and continue, since we started this, just go a little bit further out until we can begin to see the rings tipping the other way. So that in a month or so, now you can begin to see them. You can begin to see the gap there in the rings, between the rings and the planet. So from April on out, by the time we get back to looking at Saturn some months from now, it'll be back in the morning sky. So later in the year, in August, September, be up in the morning sky, we'll be seeing the rings again, not at a huge angle, but year by year as we go out from there, we'll see the angle increase considerably. So if we go out to 2026, we ought to see a pretty good tip there in the rings. So they'll be disappearing for a little while, and then they'll be back before you know it, because you won't have seen the alignment anyway while Saturn is over there near the sun. I hope you're impressed with what Stellarium will do here. This is just really, really great. All right. Let me go back to now once again and undo some of these adjustments here. All right, so those are the planet tricks. And not having an opposition isn't much of a trick for Jupiter, but it'll do. Meteor showers this year. Our best meteor showers are typically the ones that we look for, because they're the ones that produce the most meteors. There's lots of meteor showers. There's easily 1 or even 2 a month, depending on what your standards are. But most people like to go out and see meteor showers when there are lots of meteors rather than just maybe 5 an hour or something along that line. And so we tend to focus on the really prolific ones. And in that case, that means that we talk about the Perseids in August, and the Leonids in November, and the Geminids in December. Well, the Perseids are the one that most people know best because that happens in August, and we're usually not, we don't have too much of a problem going out on a nice summer night and looking for meteors. And this year, fortunately, the moon is going to be about first quarter. The moon spoils lots of meteor showers by being full, and that decreases dramatically the number of meteors that you can see, which is what people are looking for. But with the moon near first quarter, it's going to set early in the evening, and meteor activity doesn't typically pick up anyway until on towards midnight and the early morning hours, as what's called the radiant point gets higher above the horizon. And so here I've done this is a screenshot from Stellarium for about midnight on the 12th of August, which is the predicted night of the peak of the Perseids. The peaks are typically some days wide, so you don't have to be out necessarily on the 12th. But somewhere around there, looking over into the northeast, the radiant point of the Perseids, which is the apparent intersection of the Earth's motion and the planet and the swarm's motion. The meteors, we see the meteors all over the sky, but if you trace the lines, the paths of the meteors back, they will all the meteors of a particular swarm will intersect at a certain point. I should say that the trails will point back to a certain point, which is this point here in the constellation Perseus for the Perseid meteors. And it's as this radiant point gets higher above the horizon that the meteor counts, that are the number of them that we're going to see per hour goes up, and the visibility gets better. So this is the midnight here in the middle, or on the 12th of August is when we're going to see the Perseids. So we just hope for good weather then. The moon is going to spoil the other two. The moon will be near full both for the Leonids, which have been up and down anyway over recent years, but the Geminids, which have been quite productive. And in some ways, the counts on the Geminids have been going up for whatever reason, and might even be more prolific than the Perseids now. But again, this year, on the 14th of December, this year, they're going to be spoiled by the full moon. Doesn't mean you shouldn't go try to observe them if you want to, but they won't be quite as motivating for that reason. Well, so I'm going to wrap up here with something that didn't happen last year, but might happen this year. And that is the eruption, the outburst from something that astronomers call a recurrent nova, which is up in the constellation Corona Borealis. And the particular star is named with the letter capital T. So this is the actual name of a star, T Corona Borealis. Let's go to Stellarium here and see where Corona Borealis is. Now, it was up in the summer sky all last summer and into the fall, and I was checking spaceweather.com. Spaceweather does a little box where they monitor the current brightness of T Corona Borealis, T Cor Bor. But we lose Corona Borealis is kind of a springtime and summer constellation. To see Corona Borealis now, you have to get into the early morning sky. So let me just advance the hour until Corona Borealis rises. Okay, there it is. Now, here we are at, this is almost 3 a.m., basically tomorrow morning. So if you get a phone call from me tonight that T Corona Borealis has erupted, what you'll want to do is go out tomorrow morning and look for, if you know your constellations well, you'll look for this little semicircle of stars, like this. And over here will be Arcturus, which we see high in the springtime and summer skies. And over here is the constellation of Hercules. There's a nice sort of keystone shape that stargazers look for. And in between the keystone and the bright star Arcturus is the little semicircle of stars. That's Corona Borealis. So Stellarium will, of course, label these things for you if you ask. In fact, Stellarium will try to help your imagination visualize what these things are named for as well, but that doesn't much help, really. Stellarium will also help you find these things. If you're not sure where they are, you can click on, Stellarium calls it the Blaze star, and has centered it there now. So this is the star T in Corona Borealis. Well, if you look up there now, you will need a big telescope to see what's a really dim thing, about 10th magnitude, quite dim, 100 times dimmer than stars that are already too dim for you to see in the city sky. But this star here at T Corona Borealis, at that location, erupted already a couple of times. It was observed in 1787, and then it was seen in a better documented appearance in 1866, and then in a very well documented eruption in 1946, so about 80 years, give or take. Every 80 years, this thing explodes. When it does, it becomes hundreds of times brighter than it is right now, which is to say 10th magnitude, which is to say you're only going to see it in a very, very big telescope. But it is actually a pair of stars. It's a binary star system in which there's a star that is a white dwarf, a highly evolved star like our sun will be someday, the collapsed core of a star. Stars of about a solar mass will form a white dwarf as basically their remnant, their sort of their last form, a very dense, very hot, very small star core that's about the size of the Earth. And its partner is a less evolved, but more evolved than the sun, red giant star. This star has swollen up so much that its outer envelope is very weakly bound to the star itself. The core of that star is way down in there. And the envelope, the extended atmosphere of this red giant star is so great that it falls over the gravitational well and onto the white dwarf star. So this is a binary star in which matter is being transferred from the red giant down onto the surface of the white dwarf. So what this stuff is basically hydrogen, this outer envelope of the star. So the white dwarf is accumulating a layer of hydrogen. And when the mass of that hydrogen, when there's enough of that stuff, it reaches a critical density and explodes all at once, just like a hydrogen bomb. It's literally a hydrogen bomb. It's just a natural one. So that hydrogen all ignites at once, and the star becomes thousands and thousands of times brighter than it was for a few days. And then in our sky, in those previous, in 1946 and in 1866, the star became about as bright as the North Star, which in our sky is a second magnitude star. It's pretty easy to find. So it went from 10th magnitude obscurity to second magnitude for a few days, and then faded back out again, burned out all its hydrogen, but there's still plenty of hydrogen left over here in the red giant, so the cycle starts again. It starts accumulating hydrogen on the surface, then 80 years hence, we get another, or so, we get another explosion. Now, scientists who monitor very carefully the brightness of these kinds of stars, there are a few of them known in the galaxy, this is not the only one, it's just the closest one to us, have been watching the variations in brightness, what's called the light curve of this overall star, very carefully in recent years. And they saw what they thought were signs that the explosion is about to happen, the outburst is about to happen, by trying to compare it with the much less studied, much less well-determined light curves from the 1946 outburst. So we were all pretty excited that maybe this was going to happen last year, but it hasn't happened yet. The physics of these things are far from very well understood. And the physics of this particular one, of course, are not all that well known either, because you can't study them except when the outburst actually happens. So we're watching for this, because if the light curve predictions are right still, then we ought to see an outburst of this sometime in the near future. Near future in astronomy can mean a lot of things. But maybe in the next months or a year, we'll see the outburst of Corona Borealis. So you can watch for that on spaceweather.com. You'll certainly see that. In fact, if it does erupt, you will probably see it in the newspapers and that sort of thing. But you'll have to get out. Don't delay, because it'll only be bright to the naked eye for a few days after the outburst. And you see from Stellarium there that it's over in the early morning sky in the northeast. So you'll have to get out about 3 a.m. And get outside to get a look at that. So that will be the, if that actually happens, that will be the big news, not the eclipses and not the meteor showers of this year. It'll be this eruptive nova. Although whenever it goes, we'll have learned a whole lot more about these kinds of very interesting stars out there. So I'll leave you with that hope for 2025. And thank you for coming to Space Place tonight to talk about the coming year in astronomy.